So today we are going to study the electric field due to charge distribution. There are two types of charge distribution. One is discrete and one is continuous. In discrete, we have got point charges, whereas in continuous distribution, we have a group of charges which are distributed continuously over a region. And this region can be line, surface or volume. Now going to the diagram, for discrete charges, it is shown a number of point charges are shown, or the source charges, that is Q1, Q2, etc. And here we have got a capital Q, which is a test charge. And the distance between the small q and the test charge is small r. And here it is mentioned the point charges Q1, Q2, etc. up to Qn are the electric charges or the source charges, whereas the capital Q is the test charge. The small distances R1, R2, etc. up to Rn are the distances between the small q1 and capital Q. That is, R1 is a distance between small q1 and capital Q, whereas R2 is a distance between small q2 and capital Q, and similarly Rn will be the distance between small qn and capital Q respectively. So from the diagram, we have got several point charges Q1, Q2, etc. up to Qn placed at distances R1, R2, etc. up to Rn from the test charge capital Q. So the total force on the test charge due to these point charges Q1, Q2, etc. up to Qn is given as F is equal to F1 plus F2 plus etc. That is, F1 will be the force acting on capital Q due to small q1. So F is equal to, we had already discussed in the last class, F is equal to 1 by 4 pi epsilon 0 Q capital Q by R square. And here the direction is also shown by R cap. So here we are going to add all the forces resulting from Q1, Q2, etc. up to Qn. Look, it is shown 1 by 4 pi epsilon 0, which is taken as common, and inside it is Q1 capital Q by R1 squared R1 cap plus Q2 capital Q by R2 squared R2 cap plus etc. And the capital Q, which has been taken outside, that is equal to Q by 4 pi epsilon 0 into, inside the bracket we have Q1 R1 cap by R1 plus Q2 R2 cap by R2 plus Q3 R3 cap by R3 plus etc. That is, the total force F is equal to Q into, we can finalize it into capital E, that is the electric field. F is equal to Q into E, and there also we will get summation of electric fields, that is Q into E1 plus E2 plus E3 plus etc. Or E is equal to, what is it, 1 by 4 pi epsilon 0 into summation of I is equal to 1 to N Qi by Ri square into Ri cap. This is the electric field due to discrete charge. Next is the electric field due to continuous charge distribution. That is, the charge is continuously distributed over a region instead of the point charges which we discussed earlier. And this region can be a line, surface or volume. So since it is continuously distributed, our summation will become integral in continuous charge distribution. That is, whereas in point charge distribution it was summation, but when it becomes continuous it becomes integral. So electric field is equal to 1 by 4 pi epsilon 0 into integral over 1 by r squared r cap dq. So this region can be a line, surface or volume. So I think in your 11th or 12th portions you had studied this distribution over line, surface and volume. So just write the notes as an assignment, that is, electric field distribution due to line charge, due to surface charge, and a volume charge. Next is electric flux. So electric flux will be the number of electric field lines which is normal to a surface, a scalar quantity with SI unit Newton Coulomb inverse meter square. So in last class we already discussed about the different field lines and the properties. Now electric flux, which is represented by phi. Here we are taking a small area ds or a small area dA. So the flux through the small area is represented by d phi. Now in diagram we have a surface and the electric field is shown. The angle between the normal to the surface and electric field is theta. Then the flux d phi is equal to E dot ds. Now we can specify the maximum flux and the minimum flux. E dot ds is E ds cos theta. So when theta is equal to 0, what happened? The flux is equal to maximum E ds. Whereas when theta is equal to 90 degree, the flux will be minimum. That is E ds is equal to 0. And the total electric flux, that is on integration, we get phi is equal to integral over E dot ds. Then what will be the electric flux density? So we have got electric flux, then electric flux per unit area will be is equal to electric flux density. That is if d phi is the electric flux and ds is the area mentioned, the electric flux density will be equal to d phi by ds. Next we have to study what is Gauss's law. Now before that, the Gaussian surface. It's just an imaginary surface which is drawn around a charge and it can be of any size or shape. And then what's Gauss's law? So we studied what is electric flux, and this total electric flux through a closed surface will be equal to 1 by epsilon 0 into net charge enclosed by the surface. So here closed surface is taken, which is called the Gaussian surface, and we will look out the net charge of that surface, and this net charge into 1 by epsilon 0 will be equal to the total flux through that closed surface, and this is the Gauss's law. Look, the total electric flux is equal to 1 by epsilon 0 into net charge. Electric flux phi is equal to 1 by epsilon 0 into q. Let q be the net charge. Or we had already mentioned phi is equal to integral over E dot ds. Therefore, integral over E dot ds is equal to 1 by epsilon 0 into q. And this is called the Gauss's law. That is integral over, it is closed integral. It is shown a circle over an integral. It means the surface is closed. That is, the total electric flux through the closed surface is equal to 1 by epsilon 0 into net charge enclosed by the surface. Next is differential form of Gauss's law. So now we are going to study the divergence of electric field. That is, del dot E is equal to rho by epsilon 0. I think you have studied in your 11th or 12th portion. If so, just derive it and send me to the Google Classroom. That is proof of integral over E dot ds converted into divergence from del dot E, which will be proved as rho by epsilon 0.